Hello everyone. I think we should get started. I'm Louis Hagopian, I'm chair for this, and John Michael Falligant is going to be presenting on a spectrum of topics related to the dynamics of behavior. Dynamics is a broad term that is used to refer to many things, but fundamentally it pertains to change. And the study of behavior fundamentally is the study of behavior change. In our work on automatically maintained self-injury, which John Michael is going to be discussing, it's been very challenging for us to study this phenomenon because we can only begin to understand automatically maintained self-injury by examining how it changes. We examine its dynamics. We examine how it changes across conditions. And based on that, we can make inferences about what mechanisms may be in operation. So we can learn a lot about this behavior by studying how it changes. Since joining our group, he has contributed to this work in many ways, and he'll be talking about some of them today. The dynamics of behavior can be observed across many levels of analysis. Traditionally, we look at the dynamics of behavior across conditions. So if we have a macro level and a micro level, this would be, I guess, the meso level. Drilling down to the micro level, he's going to talk about changes in the temporal organization or the microstructure of behavior. This is the ebb and flow in the stream of behavior on a second-by-second basis, and its organization into bouts and pauses. So he's going to be discussing his application of a bout analytic framework to studying self-injury, which has revealed some interesting things and helped us better understand the subtypes of automatically maintained self-injury that we've described. And finally, at the more macro level, we can examine the dynamics of behavior where change is driven by selection pressures and the iteration of simple rules repeated over time where incremental change accumulates, producing complexity and divergence. So for this, he will talk about the application of the evolutionary theory of behavior dynamics and how we've applied that to the study of self-injury. The ETBED is an evolutionary algorithm that animates artificial organisms to emit behavior. This has been applied by Morris and McDowell to study automatically maintained self-injury. So he's going to be discussing a little bit of that. So I want to introduce Dr. Falligant. Thank you.
Thank you so much for the introduction, Louis. Thanks a lot. So today's talk is going to coalesce around the assessment and treatment and response dynamics observed in different subtypes of automatically maintained self-injurious behavior. So as a necessary background, in about 3/4 of cases, SIB is maintained by social consequences, things like adult attention. But in about 1/4 of cases, SIB persists in the absence of social consequences, and we call that automatically maintained SIB. Applied researchers and clinicians have long noted different patterns of automatically maintained SIB in functional analyses. We see a couple different patterns, and these patterns are even evident, and you can go back and look at the seminal Iwata paper and see evidence of these different patterns. So one pattern, we're going to refer to this as subtype 1 SIB. It's characterized by SIB that occurs at very high levels in FA conditions characterized by low levels of background reinforcement, like the alone or no interaction condition. And then in other functional analysis conditions characterized by higher levels of background reinforcement, like the toy play control, you see SIB is diminished. It occurs at very low levels, if at all. So subtype 1 SIB is characterized by a high level of differentiation between SIB and the alone and no interaction condition. And you can contrast this with subtype 2 SIB, which is invariant and occurs at high levels across FA conditions regardless of the degree of background reinforcement and stimulation present. So the contrasting response dynamic that distinguishes these subtypes has to do with how sensitive SIB is to disruption by background reinforcement. These subtype-specific differences they matter for a couple different reasons, and perhaps most importantly, you get different treatment outcomes for subtype 1 and subtype 2 SIB. Subtype 1 SIB is far easier to treat and get clinically significant reductions in with reinforcement-based procedures relative to subtype 2 SIB. There are also interesting individual differences. Individuals who engage in subtype 1 SIB tend to require less restrictive procedures. They require less protective equipment, fewer instances of applications of mechanical restraint. They also present with fewer injuries and less severe injuries at the time of intake relative to individuals with subtype 2 SIB. So this kind of begs the question, what's going on? What is accounting for this differential persistence of subtype 2 SIB? Why is it so treatment resistant? And there are more than a couple of different ideas out there about what variables might underlie these subtype specific differences. I don't want to get into a few, but here's one, is that perhaps this differential persistence of subtype 2 SIB, it has to do or reflects some kind of differences in establishing operations for SIB. The idea here is SIB is maybe controlled by different motivational variables like the magnitude and quality of endogenous reinforcement. And it may be that subtype 2 SIB produces higher magnitude or perhaps qualitatively superior endogenous reinforcers relative to subtype 1 SIB, such that alternative sources of reinforcement just can't compete with the sensory biological process of SIB for subtype 2. This could be related to something like the production of endogenous opiates. It could also have to do with pain attenuation. Yet another kind of idea there, hypothesis, is that the differential persistence of subtype 2 SIB has to do with deficits or differences in sensitivity to changes in the environment, diminished behavioral flexibility. We know that individuals with autism spectrum disorder certainly have deficits and present with deficits in behavioral flexibility. Very interesting research from the non-human primate literature. You see diminished behavioral flexibility and extinction deficits in non-human primates with a veterinary record of SIB relative to non-human primates without a veterinary record of SIB. And computational models of subtype 1 and subtype 2 in McDowell's evolutionary theory of behavior dynamics also point to differences in sensitivity to changes in the environment as an important variable that might underlie these subtype-specific differences. I should note there has been some research here directly examining this hypothesis among individuals with treatment-resistant and non-treatment-resistant SIB, and this preliminary work has found the differences in sensitivity to changes in the environment appear to be response class specific. We actually don't see a lot of differences in behavioral flexibility between these subtypes, but certainly more work needs to be done in this area. But nonetheless, this is an important hypothesis here. Differences in the degree of behavioral flexibility might underlie these subtypes. So whereas the first two hypotheses I just kind of discussed, the differences in the magnitude of reinforcement associated with SIB or differences in the degree of sensitivity to changes in the environment, those kind of point to a difference of degree and not kind as underlying these subtypes. But there's another idea here, is that maybe subtype 2 SIB is just qualitatively different. It's a difference of kind, not degree. Maybe it's not an instrumental behavior at all. Maybe it's not a form of choice behavior at all. It may be more like maybe an expression of motoric dysfunction or central nervous system dysfunction. Indeed, there are certainly a number of studies documenting an association of SIB with a variety of different movement disorders and comorbid conditions, as well as interesting neurological research and findings linking SIB to dysfunction in the basal ganglia and the limbic system. And there is also speculation that SIB, there may be some shared or overlapping pathophysiology with SIB, and that observed with individuals with complex tic disorders or repetitive behavior disorders. So this idea says it's actually maybe a difference of degree and not kind as to what is distinguishing these subtypes. So one place we can look to potentially maybe glean some insight into what's going on, what variables might be accounting for this differential persistence of SIB, is in the temporal dynamics of SIB. This has been done with other repetitive behavior disorders to learn more about the phenomenology and controlling variables of those disorders. And that's because the statistical characterization of temporal processes can sometimes give us some clues or hints as to the underlying physical basis of those processes. So everything I'm going to be talking about today in terms of the temporal dynamics is going to involve the analysis of inner response times. IRTs. And as an applied researcher and clinician, I tend not to think about inner response times a lot. I don't think about IRTs a lot. I tend to think more like response rate. Although response rate is great, we make some assumptions with the response rate that can get us in trouble and ultimately make us lose some information with respect to inner response times. When we're thinking about response rate, we're more or less assuming that all of our inner response times, all of our responses are functionally equivalent. It more or less assumes that all IRTs are generated by a single process and can be described by a single probability distribution. And just to illustrate how that might actually not be a very intuitive idea, like, here's an example. Those of you who know me know that I'm an avid Auburn University football fan. And you might observe me at an Auburn University football game, and you might be taking data on some target response of mine. Let's say it's giving out high fives at an Auburn University football game. And if you've followed Auburn football lately, you know there have been a lot of opportunities to give out high fives because they've been very good. But you might, over the course of a game, you might, from the time the game starts and the game ends, you might record my target behavior, giving out high fives, and count up how many responses I emit during the course of an observational period. You might say, he gave out 8 high fives per game. And that's more or less assuming that the IRTs for these high fives are kind of more or less perfectly spaced. But we know that when I'm giving out high fives at a football game, I don't give high fives out kind of one at a time in perfectly spaced intervals throughout the game. I give my high fives out in bouts and pauses and bursts of activity. There's not a single probability distribution of IRTs here. There's actually 2. There's very short IRTs corresponding to my within-bout responses when I'm giving out high fives, and those are punctuated then by longer IRTs. Those are, it's when I'm not giving out high fives at a game, I'm doing other things. I'm watching the game, I'm going to the concession stand to get a snack, I'm talking to people in the stands beside me. When something else exciting happens in the environment, I might engage in another bout of high-fiving, again followed by associated with very short IRTs, but then again that's going to be punctuated afterwards by a long IRT. Sometimes if you're just looking at an event record, and here there's just one I made here, times marching on from left to right, each hash mark denotes a response. Sometimes you can just look at an event record and you can see evidence of behavior organized into bouts and pauses. You can decompose these bouts a bit. You can look at and identify your bout initiation response. It's like what it sounds like. That's the response that starts the bout of activity. You can also identify the within-bout response rate. That's the local response rate within an ongoing bout. You can also identify the duration of the between-bout pause or the inter-bout interval in between bouts of responses. And you can also quantify average bout length. How many responses on average comprise a bout of activity? And what's really neat is a wealth of research from the behavioral neuroscience and behavioral neurotoxicology literatures tell us that these are dissociable elements of operant performance. As it turns out, the bout initiation rate selectively reflects the contribution of operations that affect motivational variables, changes in reinforcement rate, changes in reinforcement magnitude, operations that affect establishing operations. Those things affect bout initiation rate and bout initiation rate only, more or less. And in contrast, the within-bout response rate isn't affected by operations that affect motivational variables. Within-bout response rate reflects the contribution of variables related to the biophysical aspects or motoric aspects of performance. So operations that, for example, change the physical effort associated with engaging in a response, or operations that affect the form of the response unit. That will affect your within-bout response rate, but it won't affect your bout initiation rate. Bout length is a little more complicated and maybe a little less interesting, but bout length is thought to primarily affect or reflect changes in schedule-related manipulation. So for example, transitioning from a variable interval schedule to some kind of tandem variable interval variable ratio schedule where after you satisfy the interval component of the schedule, you also have to tack on a few additional responses to satisfy the ratio component of that schedule, that is going to necessarily increase bout length, for example. So you might see why it can be really helpful to kind of look at operant behavior through this two-mode lens and two-mode framework. And think about behavior being organized into bouts and pauses, because you can imagine, say you're comparing 2 drugs and you find that both drugs decrease some target response. They both decrease food maintained lever pressing, say. Well, through this kind of bout analytic framework, you might see that, okay, well, drug A seems to be decreasing bout initiation rates, and that tells you this must be decreasing the animal's motivation for the reinforcer. And you might see that drug B also produced an exact same level of decrease in total response rate, but if you see that it's decreasing, changing the within bout response rates, that's telling us, oh, the motivation for the reinforcer for drug B remains intact. What's actually changing is the physical dimensions of the response. Perhaps the response has just become more effortful for the animal now. So this is a method that facilitates the analysis of a variety of different mechanisms underlying behavioral persistence and change, which is potentially why it might be interesting to kind of apply this framework to study automatically maintained self-interest behavior and these subtype-specific differences. And although that sounds good, it's kind of, there's a couple of hang-ups here, and here's the chief one. Sometimes it's just hard to know and objectively define what a bout is. Like, so for example, how many bouts is this? Is this one extra long bout? Is this two shorter bouts? You could maybe even argue that maybe there's 3 bouts of activity in here. So how can we define what a bout is? Because if we can't define what a bout is, it makes it hard to measure bout initiation rates and within bout response rates. Well, fortunately, we can use a technique involving log survivor plots to define bouts based on the frequency distributions of our obtained inner response times, because we think behavior organized into bouts and pauses is comprised of a mixture of 2 distributions of inner response times. Short inner response times corresponding to within bout responses, and longer inner response times reflecting pauses in between bouts of activity. So, interestingly enough, if you plot the proportion of IRTs on a semi-logarithmic axis that are greater than some particular duration in time, if behavior is organized in bouts and pauses, you get what looks kind of like a little broken stick or a hockey stick here with 2 distinct limbs. So the left limb corresponds to our within bout responses. These are our very short IRTs. We also have a right limb that corresponds to longer IRTs, and that's going to be the pauses in between bouts of activity. And so we get a lot of good information from these log survivor plots, and in fact, if you take your right limb and you extrapolate the slope of the right limb back to the y-axis with some algebraic rearrangement, you can also estimate your overall bout length. So this is a very useful tool for analyzing the kind of bout structure and operant performance. So different operations are going to affect the shape of these log survivor plots in different ways. So for example, operations, for example, transitioning from a very dense schedule of reinforcement, like a VI 30-second schedule of reinforcement, to a relatively lean schedule of reinforcement, like a VI 8 schedule of reinforcement, is going to decrease the slope of this right limb. It's going to decrease our bout initiation rates. Another way to think about that, it's going to increase the amount of time, the duration of pauses in between bouts of activity. If you want to get even more precise than just looking at the log survivor plots, you can also fit this double exponential equation developed by Scholl and colleagues to actually empirically estimate a couple of different bout-related parameters. You can estimate P, the proportion of responses that are bout initiations. And like I said, if you take the reciprocal of that quantity and add 1 to it, you can estimate your average bout length, which is neat. You can estimate W, which is your rate of within bout responding, and you can also estimate B, your bout initiation rate. Just for me, the way that I think it's more intuitive. Instead of thinking about things as bout initiation rate, I like to think about the average duration of pauses in between bouts of activity. That is the same thing if you take the reciprocal of B, so you take 1 over B, that's the same thing as your average between bout pause, which is what I'll be talking about today. So I thought it would be neat to kind of demonstrate how we might apply this bout analytic approach to SIB data from individuals with subtype 1 and subtype 2 SIB to see if we can potentially glean or gain some type of insight into what might be going on in terms of different variables that are underlying the differential persistence of treatment-resistant subtype 2 SIB. So in terms of the data set that I'm going to be talking about today, it was obtained from a retrospective consecutively controlled case series study published in the Journal of Applied Behavior Analysis last year. All these individuals are treated on the neurobehavioral inpatient unit at the Kreiger Institute from 2015 to 2021. We have 7 individuals with subtype 1 SIB and 13 with subtype 2 SIB. And what I did was I looked at the functional analysis conditions, I looked at the FA sessions that were used to subtype these individuals with subtype 1 or subtype 2 SIB. And I calculated the IRTs for each instance of SIB that occurred in the no interaction condition and each instance of SIB that occurred in the twin play condition. I pulled the IRTs across the sessions for each condition. I subtracted off the minimum inter-response time from these distributions to get rid of what's called the response refractory period. And from there, I created log survival plots. Before I talk about what we found with the log survival plots, it might be a little more intuitive and help us build some intuition to actually review the parameter estimates from fitting Scholl's double exponential equation to these data first. Okay. So the setup for these graphs, they're all the same here. So on the x-axis, we've got our FA condition, either the no interaction condition on the left or the twin play condition on the right. This corresponds, by the way, to the mean and standard error of measurement for subtype 1 in the open circles and subtype 2 in the closed circles. So let's start with within-bound response rates. No big differences in within-bound response rates between subtypes or FA conditions, and this doesn't tell us much, but it does tell us that it seems like there are minimal differences in the physical expression of SIB between subtypes and conditions. We can also look at bound length. No differences in bound length between subtypes and between FA conditions. Okay, interestingly enough, if you look at the duration of our between bound pauses, the duration of time in between bounds of SIB, we see a significant interaction effect. So what's interesting is in the no interaction condition, the duration of pauses in between bounds of SIB are more or less equivalent for individuals with subtype 1 and subtype 2 SIB. But what's interesting is increasing the level of background reinforcement lengthens the duration of pauses in between bouts of SIB, but only for subtype 1. So this is interesting in its own right, I think, because it tells us, typically we talk about it as, the contrasting response dynamic between these subtypes has to do with the sensitivity of SIB to disruption by alternative reinforcement. And that's true, but we can actually be more specific. It's actually the sensitivity about initiations of SIB to disruption by alternative reinforcement that appears to be the key response dynamic here. Okay, so what is going on? This is very interesting, but it still doesn't exactly tell us what's going on with subtype 2 SIB. What we can do, though, is look at the log survivor plots and maybe get a little more information. Okay, so remember, if behavior is organized into bounce and pauses, you'll see, with looking at the log survivor plot, you'll see what looks like a little broken stick or a little hockey stick. That tells us behavior is organized into bounce and pauses. So I'll show you two representative cases for individuals with subtype 1 SIB, two representative subtype 2 cases, subtype 2 SIB cases, and I'll show you some data from the no interaction condition and the twin play condition. So let's start with subtype 1. So subtype 1 in the no interaction condition, behavior is organized into bounce and pauses. And for these two individuals in the twin play condition, we see the slope of the right limb is shallower in the twin play condition, and that just tells us that the bout initiation rate is decreased in the twin play condition. And that makes sense. It kind of lines up with the data we just saw. So that's subtype 1. Okay, what about subtype 2? You don't see evidence of a broken stick. That's very interesting. And I'm going to come back to this. But we see some differences in the shape of the log survivor plots for treatment-resistant and non-treatment-resistant SIB. But just to kind of tell you, I'm not just like cherry-picking some cases. I'll show you all the subtype 1 cases from the no interaction condition. What we see is more or less we see behavior organized into bounce and pauses. Just about every log survivor plot shows evidence of that broken stick appearance. And this pattern, it's evident in the no interaction condition. It's also evident in the twin play control condition. So this tells us that SIB, subtype 1 SIB rather, occurs in bounce and pauses. And this is diagnostic for choice behavior. This is diagnostic for instrumental behavior. Herrnstein in his 1970 paper says, one way to distinguish reinforced from non-reinforced responding is to look and see if it's occurring in bounce and pauses. So this makes it seem like subtype 1 SIB, that's showing evidence of reinforced responding. Okay, what about subtype 2 SIB? These are all the subtype 2 cases from the no interaction condition. And there are a few subtype 2 cases that show evidence of a nice broken stick, indicating behavior organized in bounce and pauses. But the predominant kind of log survivor plot we see looks like just a straight decreasing straight line. If you had a machine or some kind of device that just randomly spit out IRTs, that randomly generated IRTs at random, and you plotted those IRTs on a log survivor plot, this is what you would get. The steeper the line, that just means the higher the emission rate of the IRTs. So this tells us subtype 2 SIB does not appear to be organized into clean bounds and pauses. In fact, you can look in this log survivor across no interaction and twin plate conditions. This kind of log survivor plot, broken stick pattern, is about 6.5 times more likely to be observed in subtype 1 SIB than subtype 2 SIB. This also suggests that subtype 2 SIB isn't probably described by a double exponential or bi-exponential distribution of IRTs. It's probably just a single exponential distribution of IRTs better describes these data. So that also tells us we should probably take those parameter estimates I just reviewed with a grain of salt for subtype 2 cases, because a simpler model with fewer parameters would probably work just as well, if not better, at least from an information theoretic perspective. Okay, so that's interesting. So what's going on? What are the conditions? Where can we find, what's explaining this lack of a broken stick appearance for the subtype 2 cases? What kind of conditions give rise to that? A couple of different things. So here's one. You see lack of that broken stick. You see lack of behavior organized into bounds and pauses when you're dealing with very barren environments. That lack of broken stick pattern is diagnostic for barren environments. And it makes sense. From a kind of a matching theoretic perspective too, think about it. Organisms that are obtaining little reinforcement from alternative sources or from background sources are going to be less likely to sample from those sources for an extended period of time. Pigeons, for example, in pigeon research under single variable interval schedules, pigeons rarely display broken stick log survivor plots. They don't evidence two-mode responding. People looked into that. Why is that? What's going on with that? Pigeons, as it turns out, they obtain less background reinforcement and less reinforcement from non-programmed sources relative to other animals. They don't show the broken stick log survivor plot. You can experimentally observe this as well. Here are some data in panels A and B. This is some prospective translational research in this area. These are data from an individual neurobehavioral inpatient unit in a prospective study of mine. They were completing a vocational task. They're earning tokens on a VI 60-second schedule for doing something like envelope stuffing. And what you see is in conditions where there's very little background reinforcement available, the only thing they have to do is, in the context of this research study, is just to complete the task to earn tokens. They don't pause a lot from the target activity, and there's not a lot of background reinforcement to sample from, so why should they pause? As soon as we add in a lot of background reinforcement and we introduce continuous background reinforcement and we introduce continuous attention, which for this individual was a functional reinforcer, we see that behavior transitions into this nice, clean, broken stick, evidence of behavior organized into bounds and pauses. Okay, but it's worth noting, even if it does have something to do with the barren environment, that still doesn't really explain, even in the no interaction condition, which ostensibly is a barren environment, at least that's how it's programmed to be, we still see differences between subtypes in terms of behavior organized into bounds and pauses versus behavior not organized into bounds and pauses at all. So what else could be going on and underlying or contributing to this temporal organization of subtype 2 SIB? Well, one thought is you sometimes see this pattern when you have too much variability in non-target behaviors, background behaviors. When the animal is not engaged in the target response and they're engaged in other activity, there's a lot of variability in those background behaviors. That can cause considerable blending of short and long IRTs. You don't get a clean cutoff or clean distinction between short and long IRTs, and that can contribute to this single limb we see in these long survival plots. So sometimes we see too much variability can cause these problems, sometimes not enough variability. You don't have enough variation in your target and non-target responses. Highly perseverative responding, and again, some animals with like pigeons, for example, highly recurrent pecking also evidence this pattern. So variability may be an important dimension here. We can't really get a sense of variability directly from our log survivor plots because the sequence of IRTs is not important with log survivor plots. We're just looking at the overall distribution of IRTs. but we can get a sense of variability by constructing band plots. Band plots, they're neat plots where you simply display each inner response time. You either incorporate a coefficient of time into session, so you display each inner response time as a function of elapsed time in session, or you can display each IRT as a function of serial position. I'm going to nerd out for a minute, but I love this study. It's an old Blau paper, 1963. Was one of the first demonstrations of a band plot in JAB. Here we've got data from a single pigeon who was working on an FR25 reinforcement schedule, and this pigeon went through that FR25 reinforcement schedule 100 successive times, 100 successive runs on this reinforcement schedule, and each little dot here corresponds to an IRT. So there should be about 25 times 100, there should be about 2,500 little dots up here. And you can look and see and look at the IRT associated with each response in that FR run. And what I love about this is it shows that for this pigeon, once the bout of activity starts, it just goes. It lends credence to this idea that operant performance, it's kind of like a constant speed engine. Once the engine turns on, it just runs at a constant speed with very little variation. That's kind of like our within-bout response rates. It just runs. What varies is how long the engine runs for, and then once it's off, how long it stays off for before it kicks back on. Okay. So I'm going to show 3 band plots. One band plot for subtype 1 SIB, representative SIB case, and then 2 band plots for 2 different representative subtype 2 cases. So I've got my band plots on the top panel here. So we've got our IRT on our y-axis in seconds, and I've got each successive instance of SIB from a single session from the no interaction condition on the x-axis. So the first response, the second response, the third response or instance of SIB. Here on this inset panel right here, I've just got our log survivor plots for reference. Nice, clean, broken stick here. And then on the bottom panel, I've got a violin plot. A violin plot is just a combination of a box plot and a kernel density plot, and it shows the distribution and probability density of our IRTs. And what you should look for on our violin plots is where the violin plot is at its widest. That tells us that's where most of the probability density for observing a given IRT is located. So here, it's kind of hard to tell a little bit, but the fattest part of this violin plot is at the very bottom. And that tells us most of the IRTs here for this session are very small, and then you have a range of longer IRTs. And that maps on what we see in this band plot. Most of our IRTs are very short, and they're periodically punctuated by a longer IRT. So this is consistent with the idea of behavior being organized into bouts and pauses, a mixture of short IRTs and long IRTs. Okay, what about subtype 2 SIB? We don't see clear evidence of behavior organized into bouts and pauses, and at least we see a considerable blending of behavior comprised of short and long IRTs, a highly entropic distribution of IRTs. It's evident in this band plot right here. We see the corresponding log survivor plot, just evidence is a single limb, and we see, again, a considerable blending of short and long IRTs in our violin plots. So we see subtype 1 SIB organized into bouts and pauses, subtype 2 SIB, too much variability. And this is probably the modal kind of pattern we see with subtype 2, but every now and then we also see this pattern. Not enough variability. Note the scale of the y-axis here. It doesn't range from 0 to 300 seconds, it ranges from 0 to 15 seconds. Nearly every single response here occurs more or less about 2.5 seconds apart from one another. Highly perseverative responding. So you might say, oh, that's very interesting, but do these findings have generality beyond this data set, or do they have generality maybe to other classes of repetitive behavior? Well, it can be helpful sometimes to do some comparative analyses, and I can share some kind of representative data from other classes of repetitive behavior. We can talk about diurnal bruxism, motor and vocal tics in individuals with Tourette syndrome, and also data produced by organisms from McDonald's ETBD, computational models of SIB. So we'll start with diurnal bruxism, which involves, it's typically automatically maintained behavior that involves forcefully grinding one's teeth together. And major shout out, she's here, to Dr. Savannah Tate for providing these data. These are data, 2 individuals who engage in diurnal bruxism. These are data from no interaction condition. We see behaviors organized into bouts and pauses. Okay, this is consistent with instrumental activity, consistent with choice behavior, pretty clean, broken sticks here. Okay, what about motor and vocal tics among individuals with Tourette syndrome? Here I got these data from a published study by Buehler et al. 2022, who provided the IRT data as supplemental material. And this data set, it was nearly 80 children all diagnosed with Tourette syndrome, and they were observed across a series of 5-minute observations and a couple of different experimental conditions. All these individuals had Tourette syndrome and engaged in motor or vocal tics. In the baseline condition, these individuals were free to tick. There was no consequences for ticking. There was a DRO condition, which I'm not going to talk about, but in that DRO condition, these individuals could earn tokens for going 10 seconds without engaging in any ticks. And then there was a yoked NCR condition, where they could earn free tokens that were yoked to the schedule that they earned them on from the DRO condition. So non-contingent reinforcement was not particularly effective at decreasing motor and vocal tics with these individuals with Tourette syndrome. Here we've got the median and interquartile range here from our estimates from fitting Scholl's double exponential equation to these data. What's interesting is no differences in the within-bout response rate between baseline and NCR for these individuals. No differences in bout length between baseline and NCR. And adding free reinforcers in the NCR condition didn't do it much to the duration of pauses in between bouts of motor and vocal tics. Perhaps even more interesting than that, though, is just looking at the log survival plots. You don't see evidence of two-mode responding. These log survival plots, these are just sort of 3 representative cases. They look pretty similar to what we see with subtype 2 SIB. And if you look at the band plots and corresponding violin plots, you see some similarities. It seems like motor and vocal tics, they're emitted with that order of magnitude higher frequency than subtype 2 SIB, but it does seem like they share some of their temporal dynamics. There's certainly some commonalities there. A fairly striking similarity here in terms of the temporal organization of tics and what we see with subtype 2 SIB. Let me just talk about one other similarity that subtype 2 SIB and motor and vocal tics with Tourette's have in common. Has to do with something called power law scaling. A power law just means you have a relationship between 2 variables where one quantity varies as a power of another. If we plot the duration of time between instances of SIB, this is our IRT duration. If we plot that on our y-axis, we plot the logarithm of that on the y-axis. Really short IRTs at the bottom, really long IRTs are going to be at the top. If we plot that quantity against the frequency for observing a given IRT, the natural logarithm of that on the x-axis, very few instances, very many instances. What you can do is you can regress the IRT on the number of IRTs, or the frequency of a given number of IRTs. And what you see is you can expect the slope of this line. And if you have a non-zero slope, what we refer to here as K in this formula, that means we're dealing with something called power law scaling. And we see that with subtype 1 and subtype 2 SIB. What it means is, and we actually kind of get the lines look more or less like this, a negative sloped line. And it tells us that we see an order of magnitude longer duration of time between, an order of magnitude longer duration of time elapses between SIB with an order of magnitude lower probability for both subtypes. And this scaling of probability applies for both subtype 1 and subtype 2. We call this inverse power law scaling. So another way to think about it is this. As the IRT duration increases, the frequency or number of those longer IRTs decrease at a faster and more nonlinear rate for both, or for subtype 1 relative to subtype, oh, excuse me, I really messed that up. Let me start, okay. Okay, think about this. It's so confusing. I wrap my head around it. It's hard to wrap my head around it. So as the IRT duration increases, the frequency or number of those longer IRTs declines or decreases at a much faster and more nonlinear rate for subtype 2 SIB relative to subtype 1 SIB. So you see inverse power law scaling for both subtypes, but long IRTs drop off much faster for subtype 2 SIB relative to subtype 1 SIB. And this is why this matters, is because when you see that pattern and you see K values in this range for subtype 2 SIB, K values in those ranges are generated by systems that evidence fractal scaling. Fractal systems generate these K values. And it just so happens that fractal systems, and what you see if you were to plot the distribution of motor and vocal tic IRTs in the same method, you would see that there's a lot of overlap between subtype 2 SIB and motor and vocal tic and Tourette syndrome, which also demonstrates fractal scaling properties. So another kind of line of evidence here suggesting some overlap or similarities between Tourette syndrome and subtype 2 SIB. Even more direct than some kind of comparative analysis is to actually experimentally try to gain insight into the mechanisms underlying the treatment-resistant SIB. Some have leveraged principles of evolutionary dynamics to computationally model subtype 1 and subtype 2 SIB. We can create, using artificial organisms animated by McDowell's ETBD to do this. Don't have time to really get into the operation of the theory at length today, but I can kind of give you a brief 30,000-foot overview. The ETBD is a complexity theory, which means it's just a simple set of rules. And these rules are applied algorithmically, they're applied repeatedly over and over again to produce emergent outcomes that can't be known or deduced in advance. In the ETBD, the rules specifically are based on Darwinian processes of selection, reproduction, recombination, and mutation. So here's, at a very broad level, here's how the algorithm works. So the operation of the theory begins with an emission of behavior at random from a population of potential behaviors. Next, pairs of parent behaviors were combined to produce the next population of potential behaviors. And if the behavior that was just emitted produced a reinforcer, well, the parents are going to be selected on the basis of how similar they were to the behavior that was just reinforced. And so they're going to be selected on the basis of something called a fitness density function. And if the behavior that was just emitted didn't produce a reinforcer, then the parents are just going to be selected at random from the population. And once a new generation of potential behaviors is produced, then that population is going to be subjected to a small amount of mutation, and then the next emission of behavior will occur. And this process of selection and reproduction and mutation is going to be repeated over and over and over again for a specified number of generations. And what's neat is this yields a continuous stream of behavior across generations that can be recorded and studied as if it's the behavior of a live organism. So Morris and McDowell used the ETBD to model subtype 1 and subtype 2 SIB. They manipulated two things: the magnitude of reinforcement produced by SIB and sensitivity of artificial organisms to changes in the environment. They evaluated 8 different models where they manipulated these two parameters. They found that the models that best aligned or best described and was able to reproduce patterns in a simulated functional analysis that lines up with what we see with real individuals with subtype 1 and subtype 2 SIB was this. Artificial organisms with SIB that produce relatively weak reinforcement, and these artificial organisms evidence high sensitivity to changes in the environment, that produced the pattern we see with subtype 1 SIB. And in contrast, subtype 2 SIB, the model that worked best for that was one where SIB produced high levels of high magnitude reinforcement, and those artificial organisms evidenced very low diminished sensitivity to changes in the environment. You can kind of see some of these concepts or themes from hypotheses about diminished behavioral flexibility and the establishing operations for SIB instantiated in these different models of SIB here. So using their models of SIB, we simulated a functional analysis with these artificial organisms involving a no interaction condition and a toy play condition. We calculated inner response times for their instance of SIB, and we can compare the patterns that we see from the artificial organisms against the patterns we see that I've been discussing today with our clinical cases and see how well they line up. So recall with our clinical cases, we saw there weren't any differences in the within-bound response rates between subtypes or conditions. We don't really get that with the artificial organisms. We see that within-bound response rates significantly increase in the toy play condition relative to the no interaction condition. So that is kind of a failure to replicate that finding. We can also look at bound length. Recall, we didn't find any differences in bound length between subtype 1 and subtype 2 SIB, between subtypes or between conditions. And with the artificial organisms, we found a significant interaction effect. Bound length significantly increased in the toy play condition relative to the no interaction condition for subtype 1 SIB. So again, another failure to replicate that. And finally, for our between bound pauses, with the clinical cases, we saw a significant interaction effect, adding in, increasing the level of background reinforcement of the toy play condition, increased the duration of pauses in between bouts, but only for subtype 1 SIB, not for subtype 2 SIB. And we did see that pattern with the artificial organisms, so you could say we did replicate that finding. Now, it's not even clear, by the way, whether or not these artificial organism-specific differences in the temporal dynamics of SIB even matter, because ultimately they still produce the same patterns in the FA, they still respond to reinforcement-based interventions in a comparable manner as humans, but nonetheless, it's certainly an interesting question about how we might use this information to further develop and refine these models, and there have been updated models of subtype 1 and subtype 2 SIB that have come out since Morris and McDowell's original paper in 2021. It does seem like additional attempts to model automatically maintained SIB with this evolutionary algorithm might consider additional manipulations that reflect and capture this heterogeneity in subtype 2 SIB that we see. One important variable that we might also look at is how we can program in different levels of background reinforcement to better approximate the behavioral findings that we see in the clinic with humans with subtype 1 and subtype 2 SIB. One thing here is if you look at the log survivor plots, this is just representative log survivor plots from an artificial organism with subtype 1 SIB, top panel, and subtype 2 SIB in the bottom panel. You see these log survivor plots are pretty similar. They both bear some resemblance to subtype 1 log survivor plots from humans. There is a very gradual bend in the plots, and this has previously been reported by Kulabakova and McDowell. It suggests there's some blending of short and long IRTs. What's interesting, if you, and this is something that we've done experimentally, if you manipulate the rate of background reinforcement and you transition from very lean levels of background reinforcement available on an RI random interval 1000 schedule, from an RI 1000 to an RI 100 to an RI 10 to an RI 1, you see that dramatically changes the shape of these log survivor plots, and behavior appears to become organized into bouts and pauses as a function of these changes to background reinforcement. So this certainly seems like some aspect of this algorithm that could be explored in greater detail to maybe better replicate some of these temporal dynamics. So in sum, this kind of exercise tells us a couple of things. It tells us that the temporal organization of SIB appears to be a major source of behavioral differentiation between the subtypes. Increasing the level of background reinforcement decreases bound initiations of subtype 1 SIB. It doesn't affect any aspect in terms of the within-bound response rate or bound length for subtype 1 SIB, and it also doesn't affect anything for subtype 2 SIB. It's worth noting, so the temporal organization of behavior is strongly correlated with its persistence. It's unclear if it's just a mere correlate, or if potentially, and I think this is a very seductive idea, if the temporal organization of behavior itself somehow mediates its persistence. If that turns out to be the case, then that could provide a roadmap for future interventions aimed at restructuring the temporal organization of behavior and programming different interventions that make behavior become organized in clear bouts and pauses so that it will then be more susceptible to disruption by alternative reinforcement and extinction. It does seem like subtype 2 SIB, we may be dealing with a difference of kind and not a difference of degree here, just given some of these temporal dynamics. And ultimately, we hope to continue this work to just better understand these various causal and treatment action pathways for the treatment of repetitive behaviors broadly and self-interest behavior specifically. That's all I have, but I've got many people to thank, and thank you again, Dr. Hagopian, for your kind words. Thanks so much.